Hello my statics friends, welcome back. In our previous videos we've been setting up drawing free body diagrams and working to find components and resultants of vectors. Today we start to apply rules of equilibrium, and I'm going to show you where those formulas come from and how you actually start to put them to use. So without further ado, let's get started. The definition of equilibrium of forces is kind of the application of a sense of balance to a behavior or to a motion. For rigid bodies, which is what we've been studying in statics, we say that a particle is in equilibrium if the resultant of a system of forces is equal to zero. Okay, now there are other requirements, not just forces, but also moments will have to also be equal to zero as well. But for particles, since typically a particle is considered as a point, like what you see here, that if I have forces that are acting, and these can be three-dimensional or two-dimensional, acting on this object, in order to maintain equilibrium, then we could write and take a look at the basic effect of the resultant as being, for a vector p, q, and s, the resultant vector of this system, as we've learned in previous sections, is that the resultant is equal to p plus q plus s, the vectors in a vector form. Okay, and that all of that is going to be equal to some rx times an I plus ry times a j. And if you want to, you could even go in and put the third dimension on here, which would be rz multiplied by a k. And we've done that repeatedly through the series so far. Okay, now, of course, we're defining the vectors p, q, and s as being some x component of p times I plus y component times j. And then, of course, if we wanted to put the z component on there, we could as well. And the same for q and same for s, that they all have x components, they all have y components, they all have z components as we start to kind of apply those. In two dimensions, this is exactly what you would see. But if we wanted to include the third dimension, then we would just add a plus 0k on this if it were in the xy plane. But what we want to look at doing then is trying to come up with a mathematical model that represents everything being balanced. And if you go back and you look at this vector, this resultant vector that was the sum of all the I stuff and some of all the J stuff and some of all the Z stuff from this, that the only way that this is in perfect balance is if there's no net effect in I, meaning Rx has to be zero, and no net effect in Y, meaning Ry is zero, and no net effect in Z, meaning that has to be zero. So another way of writing this is that this has to be the zero vector. Okay, 0I plus 0J plus 0K. So now if we go back and kind of look at this and kind of spell out the parts a little bit differently, okay, let's take these vector pieces and drop those into the equations and look at what happens. So here I have an Rxi plus Ryj, and again, you could do Rzk on this if you wanted to. I'm not too worried about that. But if you notice, everything with an I on it in this equation was a px, a qx, and an sx. So this is px, qx, sx. Everything with a j was py, qy, sy, and that one on a j. And then likewise, everything with a z on it, which in this case would be plus 0, but could be a pz, a qz, and an sz in three dimensions, would be multiplied by a k. And if you look at everything that groups together, what you start to see is that in order for this expression to be equal to this expression, Rx has to be equal to px plus qx plus sx. Okay, and what that means is that it's the sum of all of the forces in the x direction, that all components in the x direction. Okay, likewise, the y component would be py plus qy plus sy equals the sum of forces in the y direction. And as you might imagine, rz is going to be pz plus qz plus sz is all equal to the sum of the forces in the z direction. So, and that would be everything that's happening in our z direction. Okay, and so that's what's kind of cool. Now, if we go back to our original definition that in order for equilibrium of forces to be applied, that the r vector, our resultant vector, had to be 0, then I can replace all of these terms by 0, Rx, Ry, and Rz. And so if I do that, what you're left with then is our familiar formula, from a high school physics class, that the sum of forces in the x is equal to 0, and the sum of forces in the y is equal to 0, and even the sum of the forces in the z have to be equal to 0 for equilibrium. And all three have to be satisfied for this object to be in equilibrium with respect to the forces. Now again, there are other things that we have to look at, moments being one of them, and we'll get to those here, probably in the next video we'll start talking more about those. But these are two of the three major equations of equilibrium in 2 dimensions, and this guy is obviously a 3-dimensional one. Okay, the other one that shows up then is the moments. Okay, and basically here's the idea that Newton's first law was telling us, is that a particle at rest remains at rest until acted on by an external force. Well, this is saying that if the particle is at rest, then there has to be no net force in any of these directions happening, that the resultant vector has to be 0. That's exactly what Newton's law told us back on, I think it was on day 1 or day 2 of this series. So kind of an interesting where it comes from, but it uses all of those vector addition ideas that we've talked about previously. And so we want to kind of keep that in the back of our mind as we look at this. Now, some of these problems, especially in 3D, we'll be doing it with vectors. A lot of them we'll be doing it, especially in 2D, we'll be doing with scalars. I'll show you both ways that we're going to handle those. All right. So let's talk a little bit more about this idea of equilibrium. All right. And so what we have is that for there are 2 types of equilibrium that exist. The first one is translational equilibrium. And translation is basically a displacement ability of an object to move without rotating, either up or down or in or out of the page. Okay, and so the idea that we have here is that we can turn this into our equivalence study, that all of this is equivalent to a system with a single force resultant force acting on it. And if this object is experiencing translational equilibrium, then this guy is 0. Right, and so the force vectors is the sum of all of the force vectors. That's our vector equation. And if Fr is equal to 0, this is the same thing as saying that R in the last page was equal to 0. Okay, that translational equilibrium is satisfied. So that's one possibility, but that's not the only thing that can happen. We also have to consider that what if the object isn't physically moving left or right or up or down, whatever, but it could be sitting there and it could be spinning in place and rotating. And so to be in true equilibrium, you also have to satisfy the idea of rotational equilibrium. Okay, it's an effect that causes rotation but no translation. So this thing, maybe it's moving this way, and it's rotating about some center of rotation point there. So the way that we can study that is that, well, for rotational equilibrium, it's just the same thing, that all of the moment effects on this object have to add up, and if they're equal to 0, then this object is not rotating. And so if I take, for an arbitrary object with an F1 vector and an F2 vector at their respective points, we'll define the position vector from my origin to a point on F1 and an R2 vector from the origin to a point on F2. All right, well, we know from our vector equations that the moment vector for this combined object is R1 crossed into F1, okay, plus R2 crossed into F2, plus however many others that you have. And that's going to be equal to then the M1 vector plus the M2 vector plus however many more that I have. That this guy by himself is an M1 vector, and this guy here is an M2 vector. Okay, and if this M naught totals up to be a 0 vector, like what we did with the resultant forces, then rotational equilibrium is said to be satisfied. Okay, so if we take our idea of particle equilibrium that we showed on the last page, for rigid body equilibrium, the entire package consists of 2 vector equations, that the force vector equation better be equal to 0, the resultant, as well as the moment vector equation better be equal to 0. Now, if you think about this as being something times I plus something times j plus something times k, and likewise down here do the same thing, I plus something j plus something k. You now have basically, if every one of these parenthesis terms has to be equal to 0 for equilibrium to be satisfied, you now have 6 equations to work with. In 2 dimensions, you only need 3 of them. I need the forces I, forces j, and the moment k to be able to do it, because all the others don't exist. They're out of plane. So that's kind of the idea of what we're looking at trying to do, is applying this notion of equilibrium. Okay, now in the last video, we also talked a little bit about free body diagrams. Okay, and so what this is this is the picture that has to be drawn in which we account for all known and unknown forces that act on a body. Now, if you remember, we talked about the W.I.S.E analogy, W.I.S.E. Okay, and if you don't remember what these are, go back and look at the video previous to this one. W is the self weight, I is the internal forces, S is support reactions, and E is external applied loads. Okay, and so the thing that's interesting to note is that on a free body diagram, if you don't know the value of a force numerically, but you know that it's there and it's acting in a direction, or should be, okay, the direction doesn't matter, okay, because as we saw in the last example of the last video, a negative sign on any one of these when you solve for its unknown value tells you that what you drew on the picture is backwards. Okay, so the direction or the sense of the force doesn't matter so long as we account for the fact that it's there. So if I assume it backwards, our equations will tell me and it will self-correct itself if we're careful, right? So that's what we're kind of looking at on that process. All right, so let's give a couple a try. We'll start off kind of simple and then we'll get a little bit more complex. So for kind of some basic equilibrium examples, the hardest part of this is to be able to compute or to figure out the free body diagram. And so I have a simple cantilever beam with a rigid fixed support at A. Okay, and at a distance of 2 meters from that support, I have a 1200 Newton force that's being applied to the beam acting in the downward direction. The beam itself is 6 meters long. Okay, and so let's just say that if we have this beam and it has a mass of 100 kilograms, well, 100 kilograms times the gravitational value, 9.81, would be the weight of this beam, and we could assume that it's either spread out over the length of the beam or we could lump it all at the center of mass. Okay, and so what I've done in this picture is I've actually drawn it with the mass on there and drawn it as a lump, a centroidal value or a mass at that, or a force at that location. Okay, and here in a couple of days on the videos, we're going to get into how do you figure out where that point is. But just know that for a rectangular object with the mass evenly spread out, it's in the middle is that point. Okay, but I'll show you how to calculate it when that's not the case here in a couple of days. All right, so when I take a look at this, we could go through, and so I could draw the free body diagram. I know this is a fixed support. I have to have a moment. I have to have an AY. I have to have an AX. Now again, the direction doesn't matter. A lot of times I assume our positive sign convention that is this, but not always. You know that this is X positive, this is Y positive, and then counterclockwise is positive. Okay, just to be in a habit, but on this example, I didn't actually do that. My AX, you can see, is backwards. But then again, it doesn't really matter because I can, once I have this picture done, this is the first step. You draw a free body diagram of everything. You don't cut anything. We don't want internal forces showing up on our equation. And then once I have this free body diagram, the very next step is you write those 3 equilibrium equations. So you can see that I don't know the value of the support reactions. I don't know what it takes to anchor this beam on the wall. But by writing this picture with the free body diagram, I can write the equations of equilibrium to it and just keep the unknowns as variables on here. So if I do the sum of forces in the x direction equal to 0, the only thing in the x direction is this guy, and that is a minus ax has to be equal to 0. Okay, well, if that's the case, then so I actually left off the minus sign. Okay, and you'll notice the way that I write that is I often put an arrow with a positive sign telling me what my positive direction is, just kind of as a reminder on there. So I'm assuming to the right positive, and again, that kind of follows my summation coordinates that I set up over here. All right, so minus ax is 0, so that tells me the ax force is 0. There's nothing horizontal, so that makes sense. Do forces in the y, well, now I have a plus ay, okay, minus 1200 minus the weight, and the weight was 100 kilograms times 9.81, 981 newtons on those. And so that means then that if I wrote this whole equation out, 1200 plus 981 is 2181 newtons. So here's the way the equation would be, the whole thing. Sum of forces y equals 0. I would have a positive ay minus 1200 newtons minus 981 newtons. All better be equal to 0 if that's an equilibrium. And so this tells me that ay is equal to a positive 2181 newtons. And that's the math. And it's this positive sign right here on the last answer that tells me whether or not what I drew in the picture was correct. So we assumed that it was upwards. Positive tells me it was indeed upwards. So I would write my answer as ay equals 2181 newtons. And then I would show an arrow as being in up direction for a support reaction, just kind of as a reminder that that's the direction in which it's acting. Okay, now we can do the same thing for the moments. And if I do that, if I sum moments at the fixed support, then my equation is going to look like, and I guess I should write it here, sum of the moments at A, all equal to 0. We'll go counterclockwise positive. This one was up positive. Okay, and so I get what would be a positive MA, that's the positive moment applied here, okay, minus 1200 times 2, that's newtons, this is meters, okay, minus 981 newtons times 3 meters, because the beam itself is 6 meters long and we said the self-weight had to be acting in the middle of it. Okay, and then all of that is equal to 0. Okay, and so that would be the equation for a scalar version of this. Again, my forces are vertical, so I know horizontal distances is all I need to calculate scalar magnitude. And then because I chose this as my point for my moment, this guy causes a clockwise rotation, the 1200 Newton force does a clockwise rotation about that point. That's why it went into the equation as a negative. Okay, right there. And likewise, the weight also acting down, 981 is acting at a distance of 3, and that's why it's minus 981 times 3. So with the scalars, you got to be careful about getting the positives and negative signs right, and that's about the only place that you can go wrong on this. So if I do all of my math, you'll find out that the MA is then a positive 5343 Newton meters. Okay, and so that positive value tells me that the picture that I drew is indeed correct. So this would be a counterclockwise moment, which is why I have an arrow here. And that's kind of the process and how we start to apply equilibrium for particles and for members. And again, it's just I'm doing the resultants. I'm doing it with the scalars. I'm not actually doing resultant vectors, but I'm taking advantage of the parts, that the forces in X have to be 0, the forces in Y have to be 0, and the moments about A have to be 0. And this is actually a moment about the Z-axis at location of A. Okay, and so that's kind of the process. All right, so let's try a couple more complex free body diagrams. We might not actually do the equilibrium equations on this. Let's pull that down to get rid of the glare. Okay, and we'll do something a little bit more complex. Maybe I have, a crank that looks something kind of like this, in which it's, looks like a boomerang happening here. It's pinned at B. It has a point A in which a rope is being applied, 500 newtons, and that rope is inclined at 45 degrees. And then on the bottom end of the crank, I have another rope that goes to a pin support at an angle of 20 degrees. And we want to draw the free body diagram of, say, this object. Now, again, the full free body diagram would include forces at the pin at B as well as forces at the pin here. But what you can do, and one thing about these tension-only members, and this is called a two-force member, okay? And it basically, the way that looks is that member, if I put that's my point C, there's a pin here, and then I put a piece here that's my D, that this guy is experiencing that behavior. Okay, if the object is straight and pinned at the ends, and the forces have to be axial, is a definition that we'll study when we get to trusses, but that's kind of the idea that we're looking at. And so this guy, if I choose to cut it, this is that tension example that we talked about last time, that there's an internal force that exists inside of this that's equal to the value of the pull. Okay, and so that's what I've done, is I've taken what was two, a dy and a dx, and I've cut the rope, and I've replaced the force in the rope with, instead of the two forces at D, I've now replaced it with a single axial force, FCD. And if I do that, then this guy clearly is going to be at 20 degrees also. Okay? And so that would be the type of picture that you would have for this object. And so you could figure out that based off of these distances, if I sum moments at B, the moment that this guy makes times its perpendicular distance, okay, is going to be balanced by the force in this guy multiplied by its perpendicular distance. So, even though its line of action is here, the perpendicular distance might be down a little bit, but it's very simple to be able to write these basic equations that we wrote before for this object. Okay, I could do, x components, y components, and write the equations, no problem. Okay, all right, so let's take a look at another one. Okay, let's suppose that we have, two balls, A and B. Okay, the mass of A is 2 kilograms, the mass of B is 2 kilograms, and they each have a radius of r. Okay, and they're sitting inside of this wedged, valley, if you will. Okay, the slope of the upper ramp is 20 degrees from the vertical, and the slope of the bottom is 20 degrees from the horizontal. And so what we want to do is try to draw the free body diagram for all of the parts. Okay, now this one, where we were cutting through and revealing internal forces, this one we're going to separate out and we're going to reveal contact forces. And remember, Newton's law says that object B is pushing on A, but A is also pushing back on B, equal and opposite reactions. So we can take advantage of this idea, and then we can also apply, well, what are the balls doing to the ground? And what is this ball doing to the upper support? And those kind of things. And if you imagine, this is basically a big roller if we're looking at it. So let's take a look and see what we can kind of figure out. All right, so for our first object, get this down here a little bit. In fact, I'm going to put the first page back so we can see that guy. If we kind of look at our effect, that if we take ball A, okay, we know that the weight of this ball, again, we're doing Y's on this, so 2 kilograms was the weight of the ball, so I multiply that by 9.81, then the force of the weight, this weight is going to be 2 times 9.81 is 19.6 newtons acting downward. Okay, now the ball itself, it is a roller with respect to the bottom support, and so there is a force vector that has to act at that contact point, which if you look, the tangent point of this is actually a line from the radius to here, and it continues on that direction. That gets you the perpendicular to that 20-degree slope. And so if we look at that, that force that exists on the bottom here is an F force, the effect of the sloped floor. It's inclined at 20 degrees off of vertical because the ramp was at 20 degrees, but it's pointing back to the middle of A. That's the nature of what these spheres and these circles are doing. Okay, and likewise at the top you can do the same thing. I can take a line of action through the tangent point at the contact point, and then that force lives on that line. That contact force lives on the line. Now we call T for top. Okay, and that's inclined also at 20 degrees. And that becomes the free body diagram of the weight and the support reactions. Okay, but we also have, if I pull this ball A out, there's also a contact force that exists between B and A. And that means that there is a contact, if this is my contact plane, perpendicular to that is this R force, and it's also at 20 degrees, and it's also pointing back to the center of the sphere. Okay, so that's the trick for these sphere objects or these circular roller objects, is that all of these contact forces point back to the middle of our object. That's why I wanted to kind of show you this one. It's kind of interesting as we look at that. So that's one ball. Okay, if I go and I look at the upper ball, this is ball B. Okay, it's the same game. Okay, so if we look, ball B, we're now pulling this guy off. And so I'll have a support reaction, I'll have his weight, and I'll also have the contact force between B and A. But now A is pushing back on B, so its force will be pushing up on B. Okay, so where we knew that the ball B was putting a force of R into A, because of Newton's law, is equal and opposite reactions, is putting the same force back into B. Okay, because the balls aren't going anywhere. And so this line is pointing to the middle point of the ball. And so again, it has to do with these contact points and understanding that this has to be 90 degrees right there. Okay, and so that it's perpendicular to the tangent of the circle at the contact point. Okay, and then everything else is the same. We have our force, this would be a force, we'll call it as P for the effect of the sloped floor from ball B. Okay, I have my weight, which again is 19.6 newtons acting down for this, and that's the free body diagram with all of their angles for that upper ball. Okay, I can also keep A and B together. And so what does that look like? If I don't take it apart at the contact point, well then I have an R pushing up and an R pushing back. They cancel each other out, and there's no net effect visible on that. And so my object would be basically the merger of the two from the previous two cases, except for these two R's cancel. Okay, and so the free body diagram for this one then is just like this. The weight of A, 19.6. The weight of B, 19.6. The floor force for A, pointing back at A, is here inclined at 20 degrees. The floor force for P, pointing back at B, the center of B, 20 degrees. And then the top force from the upper ramp at an angle of 20 off the horizontal, pointing back at A. And that would be the nature of how you could draw a free body diagram for that particular object, okay, with multiple spheres. So one of the things that you're going to learn in the series as we get into more and more advanced topics is it's kind of like solving a puzzle, figuring out, well, what can I start with and what can I work with? If I started with this piece, you can see we have, a whole bunch of unknowns happening on this that I couldn't solve for otherwise. But if I come to the second ball B, I know the weight. There are now two unknowns on it. It means I can solve for both of them based off of this, that we can write equations to be able to kind of work our way through that. And then once I have the R on this picture, I can move up to here, and now I can solve for the others. And that's kind of the nature of what it is that we're trying to do. It's a kind of a logic problem on how do I progress through this system of free body diagrams. So the same pattern is going to appear over and over. We're going to draw a free body diagram of the whole system. I'm going to write my equations, find what I can. And then I'm going to use techniques and tactics for, well, how can I further dissect this problem and draw new free body diagrams with different information on them? And that's what we did in this example. And then I'm going to have that free body diagram, and then the next step is always write equations for it. And that's what we're going to look at doing. And eventually, in a lot of cases, if it's statically determinate, you can work your way through and actually find all of the unknowns that you couldn't have solved for back on the original. That's the problem with this one, is I have 1, 2, 3 unknowns, okay? But I would only really have 2 equations to work with on this. And so that's kind of the nature of what it is that what we're looking to do. So I hope that's made some sense to you. Okay, all right. So let's go through and let's get that page out of here. let's go try a couple others and kind of revisit one that we had last time. So last time we had a system that kind of looked like this. I think the sloped rope was up on the other side, but this is a pretty classic starter problem for statics and equilibrium. Okay, and so what we're going to look at is, that if my mass is 10 kilograms, we want to find the tensions in cable AB and AD. Okay, last time we just looked at how do I draw the free body diagrams to be able to get it, but now we're going to actually do equilibrium and solve for these values, because if equilibrium exists, this object is static, it's not moving. And so we can go through the first step, always draw the free body diagram. So what we have is we have a rope tied at D, I have a rope tied at B, and then I have a weight hanging at C off of a ring or a pin at A. Okay, and so what we want to find is, what's the tension in the ropes if they're all tied off to that. So what we do is we can draw a free body diagram of the knot or the ring at A. Okay, and when I do that, remember, we're going to draw an isolation box around this object, and anywhere in my isolation box it has to be a closed polygon, and we're going to draw everything inside of that polygon. And anywhere that this polygon intersects a physical object, internal forces have to show up. Now, these are all cables and ropes, so we know that the force is axial only. There are no moments, there are no shears, just axial forces. And so the free body diagram of this guy then looks something like this. That there's, at my point, this is my A, there's a force acting down, which is the tension in AC, which is equal to the weight of the mass hanging off of it. So that's 10 times 9.81, 98.1 newtons acting down. Okay, I have an unknown tension AD acting to the left, and I have an unknown tension AB acting up and to the right at 30 degrees, because that was the incline of the rope. Okay, so now I've got my valid free body diagram. Now I can go do sum of forces X, sum of forces Y. Okay, and so all we do is just write the equation. So let's take a look at forces X. What do I have acting in the X direction? Well, I have a minus TAD, so that would be the second term. Okay, and I also have a positive X component. If I assume my normal sign convention, X to the right, Y up, then the X component of this guy is his value, whatever it is, times the cosine of 30. Now again, I don't know these tension values this time. We're looking to try to find them based off of, what that weight that's hanging off of it is. So this is TAB times the cosine of 30 minus TAD is equal to 0. I have two unknowns in one equation. I can't solve for them, but I know the relationship between the two of them. So that will happen. Sometimes you can't solve for anything, but let's go write the other equation, sum of forces in the Y. And what do I have? I have what would be TAB, his X or his Y component is vertical, would be TAB times the sine of 30. That's that equation, minus TAC, which is the weight of the mass hanging down, minus TAC equals 0 is the equation, and then I can substitute in 98.1 in for my value of TAC, and when I do that I get TAB sine 30 minus 98.1 newtons equals 0, and if I do the math on this, you can find that TAB is going to be equal to a positive 196 newtons. Okay, and again, the positive indicates tension, which is what we had assumed. Okay, and so that's how we start to handle that. And then once I have TAB, I can take my 196 and plug it into my first equation up here, and now it's 196 newtons times the cosine of 30 minus TAD equals 0. You can find out that TAD is 170 newtons tension. So, and that's kind of the approach that we have happening. Now, as we talked about, if you assume a direction wrong, like I say, this will self-correct itself, and I want to kind of show you on this example what I mean. All right, so let's take the same free body diagram, but instead of pulling on this, let's say that we thought that it was pushing. Okay, now again, ropes and cables you always know are pulling. This would be a pretty elementary mistake to make, but say that you just had a late night the night before, weren't paying attention at work or whatever, you drew it this way. Okay, if we write the same equations, look at what happens. Forces in the X becomes TAB cosine 30 plus TAD. Compare that to what you had before. Before, it was a minus TAD. Okay. The sum of forces in the Y equals 0. TAB sine 30 minus TAC equals 0. That's the same as before, if I could spell. Okay, there we go. Okay, so we find out that TAB is still 196 newtons tension. It's a positive value, tells me that this guy was in the right direction. Now, if I plug this into the equation like we did before, I get 196 newtons plus cosine 30 plus TAD equals 0. TAD is now a negative 170. Okay, and that minus sign is the one that tells you that this is backwards. Okay, so these guys will always self-correct themselves. And so I drew it as a compressive force, meaning it's pushing on the object, when it should have been pulling on the object, or a tension force. So the way that I write these is I'll write the answer with the sign that I get, minus 170 newtons, and then I'll write my final answer with a representation of what it really is. So 170 newtons, and I put a T on this because it's a tensile force. And we'll explain that in more detail when we get to trusses, what this nomenclature actually means. But that's the process, and what I meant when I said that these pictures will self-correct themselves. And if you got everything backwards, they all would be backwards. So there is no limit to the number of ones that you can draw backwards on this. It will always self-correct itself. Okay, so now there are some things that we'll consider later on, that when I get a negative sign, do I go back and fix my equation so that I always get a positive value, or do I keep the equation the way that I wrote it and just plug in the negative value into the equation? And I would argue that's the way that I would recommend doing it, because if you find out that it's negative, and you know that this force is backwards, what you have to do is you have to go in and you have to fix the picture. Okay, and then if I fix the picture, it means I have to fix every equation in which that term showed up. But if you miss one in the correction phase, you're done. You won't be able to get the problem to work out correctly for you. So I would argue that draw your picture once, write your equation once, and then use the value with the signs to fix the equations in the picture, mathematically speaking. So and that will save you some heartache where you forget to change one equation but you change the other, if there is more than one. Because imagine if you did, in this case, TAB and got it backwards. I would flip the arrow, I would change the sign on this one, but say I forgot to change the other one. Well, then now it's screwed up. The problem just doesn't work out the way that you would hope it would. So anyway, that's kind of the nature of what we're doing. All right, one other little one with a trick in it that I'll show you is another type of assembly. Okay, so now I've got, I have what would be a rope at A that's pinned at A that wraps around a pulley at B and then comes down to a knot at C. And then this little icon indicates that it's a spring, meaning that as the force increases, it changes in length. Okay, now for statics, we're not going to do a whole lot with springs in this. When you get to mechanics materials in your design classes, you'll do a lot more. But the basic idea is that as a snapshot in time, once equilibrium has been settled, I can go make measurements of angles and forces, and I can do the exact same static principles. All right, so at C, I have a mass that's hanging down of 6 kilograms. We want to draw the free body diagram of the knot at C. Okay, and so just like we did before, we would do our isolation box around this. Okay, this is 60 degrees. I would have a tension in the cable that goes up around the pulley. And then remember we talked about tension forces and pulleys and how they wrap around that. If I looked at the pulley, I would have a tension force that goes here, and then I would have another one that comes down here. Okay, and that we know that if this is frictionless, that if this is T1 and this is T2, that T1 would be equal to T2 on the pulley. And again, this would be pinned at the ceiling, something like that. So you would end up with a vertical force for the pin and a horizontal force for the pin as well that helps to balance all of this. Okay, and so that's all that we would have to do. The weight of this weight is still the same thing. It's a force with a mass of 6 kilograms, so I would calculate the weight due to gravity, mass times gravity, 9.81 equals 58.9, and now you're back to playing the exact same game. So what I've done is I've actually drawn this in two phases. I've got the weight by itself with a rope segment, okay, and then I've got the rope segment up here, and I've cut the rope, okay, and so here's the weight, and so I know that the force in the rope, this TCE value, has to be the same as the weight on this. So if I do sum of forces in the y direction of that guy equal to 0, that I would get positive TCE minus WE all equals 0. And if I know WE, then I can solve for the tension in the rope. And then when I go up to the other free body diagram, notice how this guy now flips directions. It's equal and opposite. Again, that's an internal force. Rope forces are always internal forces. And so you can go solve for what this guy is, and then from here I can solve for all the forces as well. So it's, just even though the apparatus looked really convoluted and messy on this, if I cut here, I don't have to worry about the spring. And if I cut here, I don't have to worry about the pulley. So how you cut these objects will greatly simplify, or conversely greatly complicate, your problem solving ability on this. So like I say, we're going to spend a lot of time in the coming lessons on strategies on where to cut and what to cut and how to proceed with analyzing a structure. But even something that's pretty messed up and complicated like this guy, I can still solve it using the same basic principles of draw a free body diagram, write the equations. Draw more free body diagrams, write more equations. It's a never-ending process, and it's constantly It's the same set of steps over and over and over. So congratulations, you now know half of the story on equilibrium. In the next video, we'll start talking about forces in space, and then we'll start applying moments and show how those will start to be incorporated as well. So I hope this has made sense to you. As always, if you've got any comments or any questions, please leave us some feedback down below, and we'll be happy to try to resolve any issues that you're having. And as always, toss us a like on the video if you found it useful, and be sure to subscribe to the channel, and you'll know when the next video comes out. So with that being said, I will wish you all a wonderful evening, and we will see you guys next time. Happy engineering.